be talking about something a little different today, oceans and carbon dioxide. He's a professor at University of Pennsylvania right now, and before that was a postdoc at MIT in their oceans group, and then did their PhD at Princeton. And I will just let her take it from that.
No, it's this here.
Okay.
Yeah. Oh. Depends on the position. So color is very important.
Pins are wonky or?
It's the charging the port. I didn't notice if she just.
I just stay here.
Pull on
Put
it
it
so it
down.
comes up. Pull on the cable so it comes more.
Try it.
You got it.
Yeah, that's the mic. Someone's here testing. How that goes.
Very good. Very good. Thanks for having me. Yeah, so Justin is in the audience. If I'm nervous, it's because of him, not because of anybody else. We usually don't go to each other talks. So I'll be talking about the role of the ocean in climate change. And I'm an oceanographer, and my work is at the intersection of physics, biogeochemistry, and ecology. So you'll hear a little bit of each today. So let me give you a little bit of background here for those of you who don't know much about this topic. So the warming of the climate system is unequivocal, as is now evident from observations of increases in global average air and ocean temperatures. So here we see the increase in global mean temperature from 1850 to 2000 something, from increases in sea level, from decreases in snow cover, melting of snow and ice, retreating glaciers in both the northern hemisphere and the southern hemisphere, thinning of the Arctic sea ice, and what we see here is the minimum, the extent of the sea ice in the Arctic. In red, the edge in the 1980s, the whole thing was covered with ice in the 1980s, and as of September 2000, only this was covered with ice. So we see from the 8 to 20 years, a retreat of about a third of the extent of the Arctic sea ice. The Arctic sea ice will probably completely disappear by the end of this century. In Greenland, they're doing agriculture for the first time. They're really, really excited about it. These are just some basics. So our knowledge of the climate system is summarized every 4 or 5 years in these so-called IPCC reports. And IPCC stands for the Intergovernmental Panel on Climate Change. And that's an association of scientists from many different countries. So in the 2007 report, the report is about 1,000 pages. It has about 1,000 contributors between reviewers and direct contributors and lead authors and so forth. It's a huge enterprise representing 100+ countries under the auspices of the United Nations. So this represents kind of a conservative view, summary view of the state of our knowledge of the climate system. And many of the things that I show you come from this kind of conservative standard view of the world. So I'm not saying anything preposterous. So the idea is that the conclusions of the latest report are that the warming is clearly happening. And there's a very high confidence, meaning they have some statistics on every word in this book, so it's 95% confidence level, that the globally average net effect of human activities in 1750 is not warming. And how do we do this warming? Naturally, we do it with the addition of greenhouse gases. Some the CO2 in the atmosphere, methane, and nitrous oxide have been increasing, right? We have put them there from year 1000 to year 2000. We're seeing this increase since the Industrial Revolution over the past 200 years. We have also put other things, such as socket aerosols, which have a different role. This is actually a cooling agent for the atmosphere. It's an aerosol. But these are the main greenhouse gases that result in the warming, and most of this warming is due to CO2, which is the primary greenhouse gas. And of course, their impacts depend on their lifetime in the atmosphere. But let me look at a tiny bit in more detail at the carbon emissions over the past 40 or 50 years, from the 1960s to the present. So then the line in black is the fossil fuel CO2 emissions, and the line in red is something else. It's called the carbon intensity of the economy. So I'll have you guess, as you see that the carbon emissions are not cleanly exponentially decreasing in time, there's some wrinkles. So I'll have you guess now, what are those wrinkles? Well, very good. Yeah, very good. Well done. So I'm just putting this to show you the effect of the fossil fuel. This is the latest data that has come out, the latest, very, very recent data to show that 2009, right, the current financial crisis in 2009 puts a big dent in the CO2 emissions, which was good for the planet. And now humanity is doing really, really well, and we're back on the track that we were beforehand. So, yeah, so humanity is doing fine. The planet, not so much. So here's a couple of, before I go into more technical details, often asked questions. So, should I care about global warming, right? So I live in Toronto, and here
Not
it's...
this winter.
Honestly, it's true. It's a good winter, warm winter. So isn't global warming going to be good for me anyway? So here, projected changes in precipitation over 100 years. So this is the difference between end of 21st century and end of 20th century, showing in blue, you see the various degrees of increasing in precipitation. So higher blues are more increases in precipitation, and higher reds are more dryness. Right? So the opposite, more relative evaporation, more dryness in the system. So the general patterns that you see is that places that are dry will get drier. Places that are wet, such as the tropics and Canada, are going to get even wetter. So the news there is that there's going to be more precipitation, most of it in the form of snow. So on long-term average, we're expecting more snow in Canada. And this is also very good news for my sister, who lives in Seattle. And she will be very happy to know that the bluest blue is in Seattle. They really like rain there. So...
Is there an easy way to know, an easy way to see why that would be? Probably not.
Yes, there is. The first order thing to think about is a law in chemistry that I'm sure at some point you have all seen, which shows that the saturation vapor pressure, if you take a parcel of the air and you think about the pressure of the air, right, is going to be equal to the sum of all the partial pressures of the gases, including the partial pressure of water. And the saturation vapor pressure of water, which is a proportion of the humidity in the atmosphere, increases exponentially with temperature. This is called the Clausius-Clapeyron law. So because of the Clausius-Clapeyron law, as the planet is getting warmer, there will be, on average, the atmosphere can hold actually more and more water. And we're going to see an intensification of the entire hydrological cycle because of that. So that's the first order. The first order explanation.
And why is that?
Then we have to think about the circulation of the atmosphere. So then it gets into the circulation pattern. So the heavy cells, which transfer heat and and moisture in the atmosphere are expanding. We're missing an expansion of both causes. So we have to understand the atmospheric circulation to understand the dryness. So we will get on average more evaporation and more precipitation. There's going to be an enhancement of the entire hydrological cycle. So the second of very often asked questions is climate has changed in the past a lot. So why is it what we're doing now, especially in any way? So to understand that, I've just put a plot of how the climate has been oscillating over the past, in this case, 500,000 years. It's really over the past 2 million years that it's been doing the same thing. So the lines in blue is CO2, the line in red is methane. And we see that the CO2 goes down and up, down and up, down and up. And the parts where CO2 goes down are more often, so the climate system oscillates between cold, low CO2 glacial periods and warm, high CO2 interglacials. So it just keeps going between these states up and down, up and down. So I redrew it here. It's obviously not done correctly for the board, but I redrew it here to give you a sense of the numbers. So CO2 is measured in ppm, parts per million volume, meaning if you take 10 to the 6 particles of air, 390 of those will be CO2. Everything else will be primarily oxygen and nitrogen, right, and other good things. So CO2 this is the concentration of it. Now, in this glacial interglacial over the past 2 million years, CO2 has varied between 180 and 280, up and down, up and down, up and down. So here comes the Industrial Revolution, and what do? Here? We put a delta spike, right? We put a delta spike of CO2 in the atmosphere. Of what amount? Well, we went from this 280 to 390, right? So we're 390, 280. So we have already put in more than 100 ppm over 200 years, right? Compared to the 200 ppm variation, right, that happens in the natural climate cycle, in the natural Milankovitch-driven cycle, on a time scale of 100,000 years. So that's why, this is the first reason why what we're doing is very worrisome, because we are putting a built-in function of CO2 in the atmosphere. So even if we don't think of absolute temperature changes, what is the most worrisome thing is the speed of change. So as a consequence of this, the present rate of warming, right, which is about less than 1 degree Celsius per century in the 20th century, but is projected to be from 3 to 6 degrees Celsius per century, depending on the model projection over the 21st century, is much higher than the rate of warming in the most abrupt periods of the transitions in the ice ages, which are about 0.1, the most abrupt periods. So now there are other periods in the Earth history when we have seen huge warming of the planet related to changes in the ocean, which is what I'm talking about today. And an example of that is an event 55 million years ago. I won't go into details of these, but big things changed and a lot of warming. Cretaceous was a particularly warm period, much warmer than today. So the Cretaceous warming. But however, there wasn't so much harm done to life during the Cretaceous because this warming happened over millions of years, basically. So there's gradual warming of the planet. So the harm to life really depends on the speed of climate change. So even in this previous geological, we haven't found in the geological record yet a period where the warming has happened at a rate that is this accelerated, as accelerated as we are projecting it for the 21st century. So this is one of the things that we really need to worry about, right? The harm to life. I mean, and by life, I mean not only us, but plants, which are less in animals and so forth, right? So then the second thing that I wanted to mention about the speed of change is that this is a nonlinear system. So it's right, we're solving large differential equations, and it's a very nonlinear system, and it's possible to have dramatic regime shifts. And abrupt climate changes. And this is a whole topic in itself with climate, so there's a subgroup of people who study abrupt climate changes. And one of these, for example, for those of you who have seen the movie some years ago, The Day After Tomorrow, whether a shutdown of the ocean thermohaline circulation or the large-scale circulation in the ocean is impossible. Is it possible even to reverse it? Have there been times in the past when the circulation went the other way around? So this is a lot of, right, this is a nonlinear dynamics kind of topic that is we need to keep in mind in the background. At present, right, this shutdown is considered to be a low probability, but high risk scenario. I mean, if this thing happens, this is bad, right? So we need to at least explore what if. So the other point is that what we're doing is different because we're changing ocean chemistry hugely. And you have probably all heard about ocean acidification. And we're expecting that by year 2100, the acidification in the ocean, pH will be lower than any time than in the past 20 million years. And that has two implications. It has implications on these guys, right? Or forms of little plants that live in the ocean that have calcium carbonate shells that get dissolved if you acidify the ocean, if you CO2 the ocean, corals, etc. But the other thing, more large scale for climate, right? Even if you don't care about these guys, we care about the climate. And the point is that the more CO2 you put in the ocean, because of the chemistry of the ocean, and I'm not going to go into details of that today, but basically you decrease the capacity of the ocean to take up additional CO2. This is a process called the buffering factor. So the presence of carbonate in the ocean makes it such that the ocean can take up large quantities of CO2. But the more CO2 we put in, the more of this carbonate we consume, and hence less CO2 is going to go in. So the efficiency of the uptake is going to decrease in time because we're putting CO2 in. So that's, I won't go through these. So here's a couple of, so these are so you can see a little bit where I fit into this and what I work on. The big questions I'm interested in are, what are the implications of climate change for the physics of the ocean, right? And then for the chemistry of the ocean and for life, right, for ecology. And what are the feedbacks in the system? And another way to frame it is, what is the role of the ocean in climate change? Right? So climate, the atmosphere impacts the ocean, which in turn impacts the atmosphere, et cetera, et cetera. So feedbacks, when you study climate science, feedbacks are a very important thing. So my research again is at the intersection of ocean biogeochemistry, physics, and ecology. So I wanted to show you a little bit where I fit into the big climate model, big climate model. This shows the evolution of our knowledge of the climate system as seen in the development of climate models. So we start in the 70s. With atmospheric models, and even before 1970s, there was a slow development, and finally we had the first large-scale global atmospheric models. Then we started putting clouds in the 80s, we started putting land surface, and a little bit of ice in a very simplified way. Then in the 90s, the ocean comes in, but the ocean is one thin layer. The ocean is one thin layer. In the 96, in the next IPCC report, the models that report their results have sulfates and have volcanic activity. So there is chemistry on that going on. And their emissions, right? There were emissions here, but now we're adding sulfates, which actually have a cooling impact on climate. So we are refining our emission model. Now in the 2001 IPCC report, there's finally a carbon on land. We're starting to have rivers, and we have an overturning circulation in the ocean. So you see immediately that the ocean, right? Oceanography is a newer science, it's very science in some sense, right? But at least in this large scale model setup. So we finally have overturning circulation in the ocean. And in 2007, we're at the report. We add chemistry in the atmosphere, and we add biogeochemistry in the ocean. Now the next report that is going to be in 2013 is going to include output from models that have for the first time ocean ecology. So I will discuss in a few minutes the results of such a model. So what I do is really here, is the new, and one of the questions here is, will these additions of the biogeochemistry and the ecology really change the response of the climate? will the climate response to CO2 emissions be fundamentally different if we add this biogeochemistry to it? And there have already been some studies on this, and the answer is yes, very much so. Including the feedbacks between the carbon cycle and atmospheric CO2 results in additional warming of the atmosphere, about 1 degree Celsius on top of 4 or 5 that we would see without those feedbacks in the carbon cycle, and about 200 more ppm in the atmosphere. So it's very, very, very important for the
So
climate.
which of the previous steps have the biggest effect?
Well, so putting CO2 emissions, right? So you
Well,
put
that-
CO2 emissions
sure.
in them,
But-
and that's it. You see it. Then what people did is they overshot. They put CO2 emissions in the 90s, and they overshot because they didn't include sulfates, which go the other way to cool the planet. So then their prediction actually of CO2 temperature increases dropped from there to there. But they haven't increased steadily ever since with the new additions of complexity in the model. So,
But the overall temperature change is still dominated by the original CO2. Everything else is some smaller correction to the CO2.
yeah, so we are discussing, yeah, so we put CO2, and now we're going to allow for feedbacks on land and feedbacks in the ocean system. And the question is, yeah, what's the relative impact of those on the system? Yes, it's good. So we have, the first order is physics, right, and some basic chemistry, right? So now we're refining our model. So what is the role of the ocean in the ongoing climate change debate? So first thing, oceans take up heat, right? And they transport heat primarily from low latitudes to high latitudes, with a big impact on the climate. Here I'm showing, for example, projections. These are different CO2 emission scenarios. We won't focus on the details, so let's just focus on this one. Let's just think of this as present and this is future, and this is future, yes. So we're seeing the temperature, this is a projection of temperature. So how the temperature is going to increase in the future compared to the present. So what we're seeing is temperatures over land, right, are increasing much more than over the oceans. Right? So why is that? Do you guys know? Why? Can you guess? So why are temperatures increasing more over land than the ocean?
Well, the ocean is a big heat capacity.
Heat capacity. So that's the first one. The first answer is heat capacity. So for a given amount of heat, right, the ocean can take up much more. The delta T is going to be smaller for the same amount of heat that you put in and it gets more complicated than that because the ocean also is mixed vertically, right? So as you put heat in, the heat penetrates further down to the water column. So while in soils, there's very little vertical mixing. So only the top ones are able to accept it.
So what's the time scale for that? I mean, I would have thought that when on like, I don't know anything about this, but I would have thought on like 10-year time scales that would all equal out. That would all even out. But is the time scale like centuries then, or
That it will all even out? What do you mean?
like that the increase in the ocean would be the same as over land? If I put in a bunch of carbon today and just waited, I would have thought that the temperature change would have been roughly the same everywhere in like 10 years. But is it more like 100 years, or because heat capacity is only buffers transients, right? It doesn't buffer steady state.
No, but this is you are constantly adding heat. There's a constant source of heat, right? So what we're doing with the extra CO2 in the atmosphere, it's as if we put an extra source of heat constantly. Actually, that source of heat is increasing over time. So at every point in time, we're going to see this.
No, I know, but I wouldn't have thought it would lag. I mean, it looks like it's lagging by like a lot. I would have thought it would lag by 10 years or so. Like there's a time scale in there, right, for it to be.
Yeah, but if you're constantly putting it in, I'll have to think a little more deeply. I haven't thought about it that way. I have to think a bit more deeply to give a smarter answer to that one. So now the next point here is that of the heat that we have put out in the last 50 years, the oceans have actually taken up most of it. About 90% of it has been taken out by the ocean. And the rest, 5% by the land, 3% atmosphere, 3% ice. So that's a good number to keep in mind, right? So the additional anthropogenic heat mostly goes into the ocean. So it's good we have the oceans, otherwise we wouldn't do that, right?
Yeah, when it goes into the ocean, it mainly goes to the heat in the ocean, not Obviously, some part of it goes into kinetic as well.
Actually, we're going to see in a second, it goes into the opposite, it stratifies the ocean, it doesn't stir the ocean. Yeah, so it's primarily, it's heat in the ocean, and this heat is taken out by the currents to the deep interior ocean, and is gradually penetrating into the interior ocean. So it's a, so then the next point is that ocean take up CO2. Right? So here's the brief intro to the carbon cycle. So you have, if we look at the net amounts of carbon, right? So this is the net amount of carbon in the atmosphere, of CO2 in the atmosphere. Numbers in red are anthropogenic emissions. Numbers in black are natural carbon cycle that existed there pre-industrial. So it's about 700 something in the atmosphere. And if we look in the ocean, most of the ocean holds 38,000 petagrams carbon, while the vegetation and soil hold about 2,000 petagrams carbon. So we see immediately from here that the ocean, right, holds 50 or 60 times more carbon in the atmosphere, much more than the vegetation. So on time scales that are long enough, which are going to be beyond decades, centuries, thousands of years, etc., the ocean is really the dominant player in the carbon cycle. So there's and the reason for that, the reason why there's so much more carbon in the ocean compared to the atmosphere, is a combination of processes which we call carbon pumps. So there are two main carbon pumps. There's a pump, something called the solubility pump, and something called the biological pump. So now the solubility pump, simply put, gases are more soluble. Gases such as CO2 are more soluble in cold waters. So this is my high latitude, right? This is the North Atlantic. This is the Southern Ocean. These are cold waters. They hold a lot of CO2. And it just happens that deep water formation, so deep water forms here, and this heavy water sinks to the bottom of the ocean, taking with it all this CO2. So as a consequence of this, so it's a combination of the physics of the system plus the pure solubility effect, the deep waters will hold more CO2 than the surface waters. So it's a temperature effect. We call this a solubility pump. The next one, which I'll go into more detail now, is called the biological pump. This is how this works. At the surface of the ocean, we have phytoplankton. Phytoplankton are little plants, right? Phytoplankton take up CO2 using sunlight. And this is organic matter, right? They're either eaten by zooplankton or they die and they fall throughout the water column. As they fall throughout the water column, they take now the CO2 incorporated into the air, right? The CO2 through the photosynthesis reaction on top, but incorporated into the organic matter. They fall throughout the water column, and at the bottom they decompose, right? So organic matter plus oxygen, this is the respiration or mineralization reaction. So as a consequence of these two equations, basically, nutrients and CO2 are consumed at the surface of the ocean through photosynthesis, and they're added to the deep ocean through the respiration or remineralization or degradation of organic matter in the deep ocean. And this is a reaction that depends on bacteria, temperatures, and et cetera, et cetera. So the consequence of this is to take CO2 and nutrients from the surface and to the bottom. And this is what we call the biological carbon.
It remains in the ocean. It's not far away from the ocean.
Sorry?
It remains in the ocean, the carbon. It's not far away from the ocean.
Some of it goes to the ocean for a very small percent. 1% of the total organic matter enters on the floor. The rest is throughout, it stays in the water column and is mixed by the physics, right? So you'll see in a second what I mean by that. So as a consequence of that, if I'm plotting nutrients versus depth, nutrients increase with depth, different types of nutrients, phosphate, nitrate, and dissolved in organic carbon increases with depth. The extra complication now is that the ocean is mixing, right? And mixing brings, there's mixing between the surface waters and the deep ocean. And this mixing brings CO2 from the deep ocean to the surface of the ocean and releases it and allows the CO2 to go to the atmosphere. So we need to think a little bit about what this mixing does. So I'll spend a few minutes on two different stories. So the first story that I'll talk about is how will ocean carbon storage change as this mixing is changing. So you do climate change, you put CO2 in the atmosphere, you change the climate, you change the atmosphere, you change the temperatures, you change the ventilation of the ocean. The physics is changing. And that will result in changes in carbon in the ocean. Right? So the carbon storage will change, and how will that feed back on atmospheric CO2? So the story that I work on is relating changes in the atmosphere and in the atmospheric circulation with changes in the ocean. So one of the big stories over the past that has come out since 2000 is that the mid-latitude jet streams, these are the jet streams in mid-latitude, the mid-latitude jet streams have moved forward. So I'm looking here at winds at the surface of the planet. So the mid-latitude jet streams have moved forward by a few degrees and have intensified, have increased in intensity over the last 40 years. And the reasons for that are complicated, and people in this building work on that and know much more about that than I do. It's a combination of global warming and also climate. And we expect such a trend to continue over the 21st century. And the question that I'm going to ask is, what's the impact of that, right, on ocean carbon? And what are the feedbacks in the system? So to understand that, we need to understand a very basic description of the ocean circulation. So this is how the ocean circulation looks like. So this is north, this is south, this is depth in the ocean. So because of this wind, of these wind jets coming out from west to east here in the Southern Ocean, there is upwelling of deep water in the Southern Ocean through the CBW, which is called circumpolar deep water in the Southern Ocean. Part of this water moves southward, where it becomes heavy and it becomes cold and salty, and it sinks. So it becomes heavy and sinks as unpractical bottom water. The other part of the water sinks as mild waters and intermediate waters further north at 40 miles and at 40 south. And then this water moves southward, diffuses to the surface, and becomes part of the Gulf Stream. The Gulf Stream moves northward in the North Atlantic, becomes cold and salty, and it sinks. And this is the North Atlantic water, right? The so-called variable circulation, this part of the circulation. So what is going to be the impact of wind, of changing in wind? So I'm intensifying the winds in the Southern Ocean. What will that do? So this is a cartoon of the same thing. So maybe I'll skip it and I'll just say 2 minutes. So what happens is that I showed you that because of biology and because of the solubility effect, most of the carbon in the ocean is in the deep ocean. So most of the CO2 is here. So simply put, if you increase the circumpolar deep water, so if you increase this, you're going to take up this extra CO2 from here and you're going to put it up into the atmosphere. So you take this CO2 from here and you put it up into the atmosphere, and you increase in the process atmospheric CO2. So you can see how, maybe I'll write it so you see it. So you have climate change, right? Let's say you've increased atmospheric CO2, right? You've increased atmospheric CO2. That has increased the winds, right? And that increase in the winds has resulted in more CO2 lost going from the deep ocean to the atmosphere. So that has resulted in additional atmospheric CO2. Right? So this is a positive feedback to that, right? That's a positive feedback to that. But now there's something counteracting this, and the story that at the same time, an increase in winds will result in an increase in the formation of intermediate waters, of mode of intermediate waters. So if you increase and the role of these in the carbon cycle is that they take up anthropogenic CO2. The new CO2 that we have put up into the atmosphere is taken back by these waters. So it's always a case in climate. It's very complicated. We always have counteracting impacts. So you have increased the winds, but the increase in winds basically acts to increase the uptake of anthropogenic CO2. So if you increase the uptake of anthropogenic CO2, right, that will decrease atmospheric CO2, and it's a negative feedback on the system, right? So it's a negative feedback on the system. So the question is, which of these two are going to win? Right? Which of these two are going to win? The first one acts on what we call the natural carbon that existed there on glacial, interglacial, long time scales, and the second one acts on the anthropogenic new addition to the system. So there are people who are taking one side versus another. This is a very hot debate in our field right now. And
so these upwellings and downwellings, these are primarily wind stress driven.
yeah, so
These are like active circulation.
so it's a combination. So the surface, yeah. So this is the reason I'm not showing it here is wind. Yeah. But it's a combination of the so-called thermokinetic temperature salinity dribbling plus wind driven at the surface. So it's a combination of these two things.
So it's by reducing the CO2, and we also shift the wind further south. Right?
Yeah.
How does that affect the
It turns out that it goes in the same direction. It turns out that it goes in the same direction because I could go into details why, but it's the same direction. The position of the winds relative to the Drake Passage, which is the place where upwelling is the best place for upwelling to happen, matters. So as you're moving the winds closer over the Drake Passage, it's actually goes the same way with increasing winds. So this is the debate, right? Will the ocean be a positive or negative feedback on atmospheric CO2 then? And what is happening? And what I work on is basically developing simple theories or not so simple theories on how atmospheric CO2 depends on the ocean carbon storage. So if you think of the ocean and the atmosphere as being the box model like this, so in which the total, so let's say we have two boxes, so the total carbon in the system between the atmosphere and the ocean is constant. If you have more CO2 in the atmosphere, you have less in the ocean and the other way around, right? So that, so if you have models, this is a control simulation in one of these GCM general simulation models that I run. This is a control simulation. This is a simulation with high winds, right? So if you increase your winds, you're going to store less carbon in the ocean, right? In my model, right? I'm storing less carbon in the ocean because this mechanism is what wins in my model. And as a consequence of that, atmospheric CO2 increases. And so we see that this should be a line like this. And I work on theories of what determines the exact curve of this line and what's the shape of this line, what's the sensitivity of atmospheric CO2 to changes in the ocean, carbon storage. So that's one direction. And, I'm doing an ongoing work with two collaborators at McGill and my advisor in Princeton to develop coupled ocean atmospheric climate learning simulations to evaluate the different impacts of the system on the different carbon pumps and to expand this theory. And what's interesting here is that we're using exactly, so we're using the same model that our McGill collaborators are using, and they're actually running the simulations are run in Toronto at the University of Toronto, the cluster here. So this is our ongoing work. The second story that I'm going to spend a few minutes on now.
So is it a global circulation model with
Yes.
the ocean in it, basically?
So it's a coupled ocean atmosphere model, running a coupled ocean.
How do you handle the change in the density of biota? I mean, the temperature increases, you get more fine tuning.
So this is the next story.
You go back and you mentioned the Drake Passage. Do you actually have the topography involved?
This is it's a full machine, the full big thing. Yeah, so it's sophisticated. So previously, see the point here is that I've done this kind of work is done in an ocean-only model, and now I'm moving towards doing this kind of thinking in and upgrading. I'm going to a fully coupled ocean atmosphere general circulation model.
How expensive are those simulations?
Very good. It depends on the resolution, and it depends on how, very good question. So, it's getting less expensive, right, to run the same simulation. To give you an idea, if you have a coupled ocean atmosphere model of low resolution, meaning low resolution for us, higher resolution for a coupled big model is 1 degree, meaning 100 kilometers grid spacing on the planet. If you do a 3-degree spacing, meaning 300 kilometers, right, a very low resolution model. 3 weeks. 3 weeks for a modern 100 to 100 year.
You're running these at SciNet.
Depending on what you put in.
You're running a SciNet, for example.
The what, sorry?
You're running these at SciNet? You're saying it's
I think so, yes, I think it's at CITA. I have to ask him exactly. I know he runs everything for Aldo McGill, he runs it here. Yeah. and he runs exactly, I run on my cluster exactly the same. We run in parallel, kind of.
Like how many nodes? Like 1,000 cores or how many?
No, so I'm running it, you don't need 1,000 cores for this one. So each stream is 45 cores. So I run on 45 cores, but then you make mistakes. So, and then you want to run 3 or 4 of them. So ideally you want to run, 4 cores, 500, say 40 something. So, with 200 cores, you're good. You're good to go, right? If you want now to run the higher resolution models that they use for the IPCC reports, in which I have the same model, but I add the land and the ice, and then I change the resolution to 1 instead of 3 degrees, that will run on 2,000 cores. So obviously they do this usually in government labs. So we use simplified versions or low resolution versions of the models, or we do ocean only, atmosphere only, etc., etc. Right?
So is the circulation handle calibrated with direct canonical simulations, or?
Yeah. So you run a 1,000-year simulation before the present, and then that's checked, right? That's checked with all the observations you can possibly handle, right? You can possibly have. So there are usually a few years of preparation before you can run the climate change simulations, and a massive amount of people behind that to get it to be realistic at the given time, right? And then I take that and I run it further, right? So there's a lot of work in calibrating the model and choosing all your diffusivity coefficients, etc., right? To make sure that the present looks like the present, as opposed to.
Is chaos the problem?
Is chaos the problem?
Is chaos a problem? You have big changes in your output based on time and everything.
Not from because there are many problems. One of the biggest problems in the ocean community is how to choose the diffusivity coefficients. So in the equations of motions, you have diffusion of heat and tracer properties and so forth. And how to the precise, we lack measurements of those. So until now, ocean models have chosen the coefficients to be constant throughout. And now last year, there was the first paper published where they vary it horizontally so the diffusivity coefficient, right, has to do with in some sense you are parameterizing turbulent transfer, right, from one area to another. So how do you do your diffusion? It's really, we got the direction down, but how do you do your diffusion? How do you choose numerically, right, what schemes you choose, etc. And what's the choice of diffusion?
Sorry, but are the initial conditions, are your results still sensitive to initial conditions or not?
Yeah, so what they do for, I don't do that, but what they do for the long climate change simulations is for the IPCCs, which are the top notch, the whole lab of 100 people works on one of these, is they do 10 multiple simulations from slightly different perturbed initial conditions, right? And then when you present the result of your model is the mean of many of these. So yes, this is a topic that they're right.
The vertical dependence of temperature and concentration of salt and so on are well measured at different locations.
That one, yes, that one we know. That one we know, right? I'll get to the equations. I'll put up the equations in a bit. Yeah.
When you say diffusion coefficients, is it carbon diffusion or heat diffusion?
No, for everything, yeah.
For everything.
Yeah, it's actually the same. Yeah, for most things it's get the same, yeah. So we're diffusing it the same way that, yeah, for everything. Your K, del squared terms are the same. So let me show you this one because I'll have a few slides. I want to go for 5 minutes to do this and show you a few equations just so you have an idea of how they look like. So the second line of what I do is what's the impact of the climate change on ocean biology? It's a newer interest for me. And what will be the feedback on atmospheric situation and climate? And I'll show briefly a few results from one of these papers where I'm noticing that there's an asymmetry in the northern hemisphere and southern hemisphere response to ecology and biogeochemistry to climate change. This is a review now. So the usual way that we can tell what happens to ocean biology is by looking at color from satellite. So this shows areas of high chlorophyll, meaning high productivity of phytoplankton, right, and low productivity of phytoplankton, briefly speaking. So if we were to say, how has ocean biology changed over time, what we do is we look at this kind of maps, right? The problem, of course, with satellites is we don't have that much data, right? It's 20 years at most that we have. So people have looked at that, and the question is, has ocean biology and productivity increased or not? If ocean productivity increases, that is good, right? Because photosynthesis, plants take CO2, so we want that, right? Well, they're contradictory results. Some people claim to have seen over the last 2 decades increases in phytoplankton chlorophyll, sometimes decreases in phytoplankton chlorophyll, with sometimes the same person contradicting themselves. So there's a new set of studies out there that are showing that we might need about 40 more years of satellite color data to detect an anthropogenic warming signal, right? That is very worrisome for those of us who write, proposals for NASA, because right? We were telling them you need to continue to fund us, and we're going to tell you we need 40 more years for it to become relevant to us.
What's the total ocean biomass compared to land biomass?
Ah, very good. Very good. So why should we care? Yeah, why should we even care in some sense? So, yes, so if we look at the total biomass, right, meaning organic carbon, you look at the tree, what's the biomass, you weigh them. Ocean biomass, meaning all these phytoplankton guys, are less than 1% of the total biomass. However, so from that point of view, they're irrelevant, right? However, they're tiny, right? They're invisible. You look at them under the microscope. The ocean is full of these guys, but you have to look under the microscope. However, when we look at productivity, so productivity is measured in what? Productivity is measured in petagrams carbon per year, right? So it's photosynthetic uptake of CO2 from the atmosphere, photosynthesis, right? Then you look at net photosynthetic production on the planet. Half is in the ocean, half is on land.
Well, the ocean biomass just sinks to the bottom.
Exactly, and stores in the ocean. So these guys are tiny, 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 but they're mighty. Right?
But they don't live very long. But they don't live very long.
Oh, but they're constantly replaced
That's
by
the
new
point.
ones. They're constantly replaced. There are times when they're tiny babies, right? And they sink and they're taken up. Textile biology are extremely, extremely fast. And they keep sinking into the ocean, taking this carbon with them, right? So so it's half of the productivity ocean, half on land. So anyway, the point here is that global models rule. They're very important, and that's why we study them, because with satellite we can get to changes in biology. So here's how a model looks like. So here's your atmospheric model, right? You have thermodynamic equation, radiation, equations of motion, turbulence parameterizations, clouds, water conservation laws, etc. Some chemistry that I left out. In the ocean, you have equations of motion, thermodynamic, turbulence, salt, sea ice, chemistry, etc. You have a land. You have changes. You have constant exchanges of heat and water, right? And gases, CO2, oxygen between the ocean and the atmosphere. So it's very complex. So here's how the equations look like. So these are the physics equations for the atmosphere. So the physics equations are the Navier-Stokes or Reynolds equations of fluid flow, where you have a total derivative of the velocities. U, V, W are velocities in the three directions. So we should have written in the coordinate. So you're all probably confused.
We're probably, we're actually.
Yeah.
But you're new there as a turbulent viscosity, I guess.
So this is for example, this is the frictional force, right? So this is a diffusion type parametry, turbulent diffusion type parametrization. This is a pressure gradient force. And these are the Coriolis terms. This is gravity. So some of the forces. This is Newton's second law right there. Then we have an equation of state. Then we have a mass conservation equation for the density that we write in terms of the density of the flow. Then we have a thermodynamic equation, right, an energy equation for how the temperature changes in the atmosphere. So there's a thermodynamic equation. And if we look at this system and you count the number of unknowns, the velocities, U, V, W, pressure, density, temperature, blah, blah, you have an equation of 6 unknowns and 6 knowns, right? It's actually a bit more complicated. I left the water part out. There's another equation for water and humidity. And but it's a closed system, and we can solve it, obviously not analytically, but numerically it can be solved. Additionally, you have a conservation tracer equation for each of the chemical tracers considered in the atmosphere, right? So if you have CO2, nitrate, you have conservation tracer. In the ocean, it's the same thing, right? Except the conservation law, the temperature law looks a little different. You have an equation for salinity. Your continuity method a little bit different. But that's pretty much it. Then you have conservation. For each chemical tracer in the ocean, you have a conservation law. So how does the biological model look like? So now on top of this chemistry and the physics, you add the biological equations. So for the ocean, right? So what we do is we have multiple species. So we have small phytoplankton and then large phytoplankton and a third phytoplankton. And these terms here incorporate advection and diffusion. And the physics is included here, basically. These guys move with the water in all directions. Then you have a growth rate, and this growth rate is a complicated function of temperature, light, and nutrients, which change with the physics, right? So as you change the climate, you're changing all these terms. Then there are mortality terms, and there are different complicated mortality terms and forms of the mortality terms. These guys are eaten by the zooplankton, so they're eaten by the, grazed by the zooplankton, right? With a given law, right? And there's finally nutrients. There's nutrient input, that's physics, and then the nutrients are eaten up by the different phytoplankton groups. The main difference between these equations and the physics equations is that biology is empirical. Right? So when I write the specific law for the grazing, or when I write these sophisticated expressions for the growth of this is the specific growth, right, of the phytoplankton, which is a product of a temperature function, some exponential function, etc., etc. These are empirical equations, right? So that's why, in some sense, that's why they're such a late addition to the models. This is where a lot of the development will be going on in the next 10 years, because we really know very little about this, right?
So these are all equations for things that passively float. Is there anything that swims, and is that can that actually change the budget?
Yeah, that's the next step, not yet. Not yet in these models. Of course, there's a whole community of ecological people where they already have, right, they do little models of ecology. And we take these and we put them in the big models. We don't have swimmers yet.
So, empirical, does that mean that with climate change we're going to enter a parameter space where we don't know how the biology respond?
Yeah, so exactly. So part of what I do is I study the response of this ecology to the changes in physics, meaning the changes in the temperature, the changes in light, and the changes in nutrients that come with climate change. And I study the different parameter spaces.
She's where your fitting functions are.
With the fitting?
Well, you fit these things very.
Some of these can be put down.
Yeah, I mean I take these equations from people who have studied them for a long time, right? From ecology.
But at a given set of temperatures and densities, if you change things, the question is, do those fitting formulas are still going to work?
Of course, yes. And that's one of the questions that I'm interested in, for example, is how to do pollution in this kind of models, right? Can I just say that, okay, see, these forms just mean that you're going to have a nutrient dependence, that your phytoplankton growth increases up to a saturated point with nutrients. And is that form, can I just say that through evolution we're going to change, this coefficient K is going to change? Or, right, so how do you incorporate more sophisticated, right, biological concepts into this kind of physical framework?
But a lot of the biological stuff is down in laboratories.
Yeah, this is lab, like the coefficients in lab, everything comes from lab, right? It's a whole, right, there's a whole science of ecology that's like behind this, right? And then you plot these things on different grids and so forth, and I won't go through that here. But let me just show you a couple of results from one of these sophisticated models that has multiple phytoplankton groups. We have large phytoplankton, the diatom, small phytoplankton, and they have different functions in the carbon system. And they're very colorful. But just so you see kind of how these experiments go. So usually you run two sets of models. You run a control and the climate change simulation. You see your atmospheric CO2 going up, your temperature going up, the salinity going down, right? Salinity going down. So more water in the system, right? More freshening overall. More glaciers melting into the oceans, the salinity of the oceans going down. what we're seeing is that I'm showing here the wind stress at present and a change in the wind stress over 100 years. My model shows a shift southward of this is just the delta, a shift southward in the wind stress and an increase in the magnitude of that. And the impact of that shift is on the vertical velocities because the curve of the wind stress gives you the vertical velocity at the surface of the ocean. So the vertical velocities are in the ocean are going to basically in the southern ocean is going to increase. So you're going to have more mixing because to a first order it makes sense. You mix more, you have stronger winds, hence you mix more. So then you look at what's called stratification, and that's a typical thing that oceanographers look at. So this is the temperature. This is how temperature looks like in the warm ocean. Let's say in the temperate and tropical. You have warm temperatures at the surface, cold temperatures on the bottom. That means that when you translate this temperature plot and a density plot, you have light fluid on top of heavy fluid. That's a stably stratified flow. Right? Now in the high latitudes, the opposite. In the high latitudes, the temperature is very low, and the flow is not, and the fluid is not very well stratified. So the stratification. So we say that the tropics are well stratified, the high latitudes are well mixed. So the question is, what happens with climate change? What happens with climate change is the ocean stratifies even more. Basically, you're moving this temperature from here to here. You're putting even lighter, you're making the surface fluid even lighter. So you're increasing the stratification of the ocean. You're making the ocean mix less. Now, the trick there is that because most nutrients are in the deep ocean, if you mix less, it means that you bring less nutrients to the surface. Right? If you bring less nutrients to the surface, your phytoplankton won't be as happy. So if you mix less, your phytoplankton won't be as happy. So now I'm going to...
I have a question. I mean, so are insulating the surface more, you're going to lose more water, which will tend to produce higher salinity at the surface.
That's
That
the
not temperature's going up, you're going to evaporate more water at the surface. So that'll concentrate the salt in the warmer layers. So it'll tend to counteract this a little bit.
Yeah, it will counteract a little bit.
So but that's included, it doesn't.
Everything we have, right? The density goes the other way also, right? It's included.
Right, exactly.
Yes, it counterates a little bit. Sure.
How well calibrated is the turbulent messing in these stable stratified fluids?
Yeah, so that's a whole sub-area of research, right?
Right.
There's a whole sub-area of research. There was a,
But
yeah,
can you
it's a very
actually,
difficult
is this
area.
something that we can actually begin to measure in the ocean?
Yeah, so they go into the ocean and they put SF6 is called the name of the
Sulfur hexafluoride.
yeah, exactly, and they drop it in the ocean and you see it, right? And they come and they look in 1 week versus 2 weeks versus a month, is it still there, right? And they measure the rate of dispersion of these tracers. But of course you do it in localized areas. How do you extend that everywhere? So
Do they do it at depth as well as near the surface?
yeah, so there is an assumption. It's actually in the models we assume that it increases with depth. So mixing with bottom topography, for example, is supposed to increase depth. Tidal mixing is
But
supposed to
that hasn't
increase
been
that mixing.
measured directly.
I don't know exactly the answer to that one. There is, of course, there are some isolated measurements, but how, right? How, yeah. It's a lot of thinking into that. That's one of the biggest questions, yeah. So the idea here is that what is the impact of this on the phytoplankton? So I'm going to skip this and I'm just going to show you my last results slide. So basically, what I'm claiming here is that I'm seeing different responses in the southern hemisphere versus the northern hemisphere. So in the southern hemisphere, let me start with the northern hemisphere. So I'm showing time series 1840 to 2100, and I'm showing the global average is shown in black, and the northern hemisphere average is shown in green. So I'm seeing that as you're warming the planet and heating up the surface of the ocean, you're stratifying more the ocean at the surface, right? So you're stratifying more the ocean by the argument that I gave you. As a consequence of that, you're mixing less, you're bringing less nutrients from below, so your surface nutrients are dropping. As a consequence of that, phytoplankton are not happy. They don't grow as much. So the total biomass of phytoplankton goes down. As a consequence of that, the total primary production goes down. The total export flux goes down, and this I won't go into that. So how much biomass is exported below 100 liters also decreases. So this, if I just look a little bit at that green line, right? This green line is a positive feedback on the system. So you increase the temperature, you increase acidification, your nutrients decrease, your production decreases, you export less carbon to the deep ocean, right? And as a consequence of that, you're left with more CO2 in the atmosphere. So the biology in the northern hemisphere and in the global average acts as a small positive feedback on atmospheric CO2. However, my story in this paper is that the southern hemisphere is a bit different. And the southern hemisphere is different because winds are increasing more in the southern hemisphere. Right? And again, winds are increasing because there are changes in the atmosphere that make these winds increase. Ozone depletion and temperature differences between the stratosphere and the troposphere are increasing the winds. And this increase in the winds acts to mix the water more in the southern hemisphere compared to the north. So the net increase in the southern hemisphere in stratification is not as pronounced. Nutrients are not decreasing as much in the southern hemisphere. Total biomass is not decreasing much, is no change. And actually, if I look at it in more detail, I can see that the total primary production actually goes the other way. I'm not going to show you the details of why that is, but basically, it turns out that when the water is very turbulent, large phytoplankton are preferentially grow over small phytoplankton. So the large phytoplankton, the diatoms, become bigger and bigger and bigger and grow in turbulent conditions, high mixing conditions. And that's a whole physics argument as to why that is, because of their relative area over volume and so forth. So these guys grow much faster, and the size distribution of the species changes, and as a consequence, the total primary production actually increases. So the point is that the story is complicated because the southern hemisphere goes the other way. So that's so the summary for this story is that the responses are different in the northern and southern hemisphere because biology is driven by competition between stratifying effects of temperature and hydrological cycle and these stratifying effects of increasing winds. That's the large-scale story there. So here's the take-home messages for today. Do I have another one? One more. And that's it. So this is your take-home message for today. So the oceans are a net sink of carbon. However, it turns out that the efficiency of this carbon sink has started to decrease. And some models are already predicting that the efficiency of the ocean carbon uptake will continue to decrease in the next 100 years. And here are some of the reasons why. A warmer ocean will hold less CO2, so this is a solubility argument, right? Now I'm going to give you a chemistry argument. The ocean acidification increases, and as we put more CO2 in the ocean, this decreases the capacity of the ocean to further take up CO2. And there's some chemistry equations there that I'm not putting in. So that's another argument, another mechanism. All of these act on top of each other, right? And then the third one is that the story about the winds. As southern ocean westerlies are increasing, this will result in a loss of carbon from the ocean to the atmosphere. And I think that this effect is more important than the counterbalancing effect of additional anthropogenic CO2 uptake. So this is another one. And the second one is that in the global average, biological productivity is predicted by the models to be decreasing. And that means that the ocean will hold less carbon, more will be in the atmosphere. So all of these are positive feedbacks on atmospheric CO2 and reasons why I think that the efficiency of the ocean carbon sink will continue to decrease in the future. And this is my last slide. I just wanted to mention a few other directions in my research. I work a little bit on anoxia in the oceans. Anoxia is a big problem, right? With climate change, as you stratify more the ocean, less oxygen penetrates into the ocean, and that's bad for organisms, zooplankton, and other things. It's changing the biogeochemistry. So I study the relationship between physics, how changing mixing coefficients and diffusivity coefficients affects the extent of anoxia. I'm interested in paleoclimate and climate on long time scales, so I'm interested in abrupt climate change. So I study the physical processes of carbon feedbacks and abrupt climate change events observed over the past 100,000 years. This is in a simple box model theoretical framework. And I study ocean blooms. So phytoplankton are changing, and how can we predict the behavior of the blooms with climate change? And this is more of a mathematical study than this is a more theoretical approach. So I guess this area is called mathematical ecology. So thank you very much for having me here.
Couple quick questions.
Yes, so you showed us this asymmetry, or this difference between southern and northern hemisphere. Eyeballing the graphs you showed, most of them are really like the global is like the mean, whereas primary production, for example, is dominated by the northern sea and export floods. So is there a very simple reason to explain this? Or what does global mean actually? Is it not just the average of both, in the naive way, both simulations? What is the reason why it is?
I forget. I did it some months ago, and I forget right now the second. I looked at that. I was puzzled by that, but I think it's correct. There was a numerical reason that I found for it. Yeah, I'm not really. I have to think a little bit about that. And I know I thought about it at some point. That's a good question.
So I have a question. So I'm guessing you've played around with the effect of different turbulent perturbations.
Yes.
But of course, on scale, you're not going, you can get sort of anti-friction effects rather than just friction effects. Right? Increased barometric instability, or from local differences, horizontal differences between driving jets and these kind of things. And do you expect those things to matter much, or is this kind of a question earlier? Sort of kinetic energy on smaller scales, we will just act, we don't really care, it's all just heat we're dealing with, or are some of those dynamical things actually a big issue?
It depends for what, right? I mean, it depends for what, big issue for what.
Well, feedback seems to, of course, be kind of work.
Yeah, the answer is I've worked partly on these things, but I don't know enough. So for example, here I showed like 1 million plots here. So what I do in these models is I have a control simulation, and then I have simulations in which I change either the what we call isopycnal mixing in the horizontal direction, or mixing in the vertical, diapycnal mixing with lucidity, so the different coefficients of the lucidity tracer. So I change them in different ways, and for example, I see that if I increase vertical mixing, that's equivalent in the global large-scale average to increasing the winds for the general circulation. So I change the mixing in a similar way in the entire ocean or in the Southern Ocean. And then I look at large-scale changes in the circulation. Right? So then I run it, right? These models are actually, I didn't go into the details, but these are long-term simulations. I'm running each of these models for the 5,000 years simulations, each of these dots here. And then I'm looking at the integral effects of that on the large-scale circulation. But of course, yes, it's all these diffusivities are important, and they're important. It's a big field on its own, right? They're important in a zillion. There's one picture I will show you that like to illustrate this is the same that I showed before that illustrates the importance of mixing. So one of the things that happens if you change the mixing, for example, that I noticed, and it's a big discussion in the community, is what is the role of eddy transfer of heat and CO2, right? What is the role of this, the net role of the turbulent transfer? So it turns out that this is how the main flow driven by the winds looks like. But if you look at the transport of heat by if you look at the transport of all properties by the eddies, and the circulation that is driven just by this small scale diffusion transfer, it actually goes the other way. So it opposes the main flow, right? So now it turns out that if you go, I mean, I'm not going to go into all these details, but if you increase the winds, you're going to increase the mean circulation, both the blue and the red circulation. But the eddy circulation and the turbulent circulation in the ocean is actually going to oppose it, and it's going to move in the opposite direction. So one of the questions is, are these going to compensate perfectly? Or is the mean circulation going to be more important than the change in the turbulent motion? And which is going to win, right? So that's a very, very active area of research.
yeah, woman.
So you said that it was mainly the increased wind in the southern hemisphere that was mitigating some of the increased stratification. In the northern hemisphere, you also have the Arctic Ocean, which is a positive feedback, right? As we lose ice on top, water absorbs heat faster than ice does, so the Arctic Ocean heats up faster. Is that also? Is that
yes, but I was only, that's a huge news. So the ice albedo feedback is hugely important. It's a first order of magnitude. I should put it on one of the slides. But I was only mentioning the carbon feedbacks in the system. This is not a carbon feedback in the system. The ice albedo feedback is a purely physical feedback in the system.
But
it's hugely important. It's first order. Even before all of these.
But wouldn't it also increase the stratification because you're going to heat the surface faster in the north than in the south because you've got this positive feedback loop that you've lost the ice cover? So is that going to increase is that another thing that's increasing stratification in the north compared to the south?
Yeah, but is it increasing it exactly where it matters, which is here, where CO2 penetrates? Might increase it in parts of the Arctic. I haven't thought about it. I don't know. I have to think more deeply about that. Why the Southern Ocean is important is because this deep water formation happens here, and this upwelling happens here. So to a first order, if you want to think about carbon on 100 years or beyond, the Southern Ocean is like the number one and two.
Well, why is most of the plankton, I mean, just like mentioned near the poles?
Why is most of the plankton near the poles? It's not actually, if you look at the satellites, right?
I know there's also the equatorial strip, but...
Yeah. So why is it there? Very good. So it's there because in the tropics, what happens in the tropics is that the tropics are well mixed, right? So therefore, you're not bringing enough nutrients from below, right? So these are areas that have very low nutrients, right? So these are nutrient limited areas. There's not as much nutrient going on, but actually there's enough for that.
So
to average it.
What physically are the main nutrients and where are they coming from?
So the most nutrients in the ocean are in the deep ocean, right? They're in the deep ocean because of this biological pump. You produce the organic matter at the surface, the organic matter falls and it dies, decomposing back into these nutrients. So you end up with most of the nutrients residing in the deep ocean. So if you have a profile of the nutrients, you have most of them in the deep ocean. And then physics comes in because the more you stratify in parts of the ocean where you're very stratified, you can't bring these nutrients up. Hence you have less biology.
Question. You mentioned it's increasing the temperature, we are increasing mixing with the southern oceans, for example, because of more wind. And then you have more productivity. But we have enough nutrients in the southern ocean currently. There's not the productivity that we expect because of the iron. There's not enough iron there. So how does
you know subtleties. You know subtleties in the system. Yes, so it's more complicated than what I said. I didn't go into all the details. So the main thing that I'm seeing happening is that in frontal areas, at this frontal area in particular, right, the system seems to be driven by this frontal area here, which is called the subpolar subtropical subpolar transition. This area here is an area where you have very complicated physics, frontal structure in the ocean, large temperature gradients and so forth. And is dominated by these diatoms, by this large phytoplankton. So it's dominated by larger phytoplankton. And that's where an increase in upwelling and an increase in mixing will actually have a large impact because it will preferentially result in this diatoms growing more than the large phytoplankton, than the small phytoplankton. And the large phytoplankton sink more and take more carbon with them. The second part is that you have an increase in temperature, actually, that I didn't discuss here. So actually, the increase in temperature here at this location is very, very critical. So the increase in temperature results in phytoplankton growing more. Right? So it's two things. It's the competition effect and it's the temperature effect. There's also a light limitation factor that I didn't discuss here that's major. Productivity here, there's plenty of nutrients, but phytoplankton are limited by light. So it turns out that with climate change, both here in the northern hemisphere, it turns out that with climate change, the phytoplankton will end up living in a smaller part of the ocean like right next to the surface, because you're changing the shape of the temperature of the density structure in the ocean. So you're pushing the phytoplankton. The phytoplankton will see on average more light. So the phytoplankton become less light limited at the same time. So you're increasing light exposure, you're increasing the temperature, and you're preferentially growing the diatoms or the small phytoplankton. And because of the geometry of the system, these impacts are stronger here than there. And also because of the fact that the increase in winds happens in both hemispheres, but is more accentuated in the southern hemisphere, which is a physics story. Maybe the atmospheric people can explain to me why that is. The Hadley cells, the atmospheric circulation shells, are shifting in both hemispheres. The shift is larger here. The winds are increasing. The increase is larger in the southern hemisphere, etc., etc. So it's complicated, yeah. It's more.
Okay, well, with that, let's thank her again. And let me